Now, the other type of elastography is shear wave elastography. It's a very different mechanism. Unlike static elastography, where manual pressure is applied by the sonographer, and while the pressure is being applied, the color map, the elasticity map, is generated. In shear wave elastography, the sonographer simply scans the breast. There is no need to apply pressure. You're holding the transducer just as you normally would. And when you activate the elastography mode, a high-intensity ultrasound pulse is transmitted into the breast by the transducer itself. And then in real time, a color map of tissue stiffness is generated. So the shear wave is generated within the tissue, utilizing a high-intensity ultrasound pulse, and then the resulting shear waves are imaged and an elasticity map is generated. So just to go through the different mechanism of static elastography versus shear wave elastography, with static elastography, the sonographer applies pressure with the transducer, and while applying pressure, watches to see how much the lesion deforms or changes appearance. Shear wave elastography looks at a completely different property. A high-intensity pulse is transmitted into the breast tissue, and that pulse generates lateral shear waves, similar to if you see drops of water falling into a pond. Instead of looking at what happens to the pond right underneath the droplet, we're looking at what happens to those lateral ripples that spread out on either side of that pulse. Now, shear waves move extremely quickly through tissue, and this has been what has limited this modality until recently. You need an extremely high-fast system to image these shear waves. These shear waves move at a speed that is related directly to Young's modulus of elasticity. And Young's modulus is a measure of elasticity. It's actually a ratio of stress to strain. In other words, for every material, including breast tissue, there is a ratio of how much it will deform under stress. The elastic modulus is expressed as units of pressure in pascals. And for those of us who don't want to remember so much physics, very simply, lower numbers are softer tissue, higher numbers are firmer tissue. And then, interestingly, fluid does not propagate shear waves at all. So any structure in the breast that is fluid, such as a cyst, will show up as a signal void. It has no elasticity value. Here's a phantom with a completely isoechoic mass within it. And when the elastography is activated, you can see that it shows up. This happens to be stiff. It shows up very, very clearly against the background of soft material within the phantom. Now, shear wave elastography is also quantitative. So unlike static elastography, which generates a color map based on a sonographer's pressure, this is a user-independent modality that actually provides a quantitative measure of tissue stiffness. There is a bar at the side of the screen which gives you the actual measure in kilopascals of the tissue stiffness within this box. In general, normal tissue, fat and glandular tissue, will be generally less than 70 kilopascals. Malignant tissue will generally be higher than 100 kilopascals. So how do we do transient shear wave imaging? Again, just as an image to keep in mind, similar to dropping droplets into a pond of water, the transducer generates a high-energy ultrasound pulse, and then it very, very rapidly images the lateral shear waves that occur as a result of that pulse. So here's the pulse that we apply. This is the direction of propagation of the high-energy pulse transmitted into the tissue. But here's what the transducer is then looking at, is these lateral shear waves that occur. So how actually do you do this? Well, while you're scanning, you identify your lesion, you optimize its appearance on your B-mode images, you activate the elastography, which is simply a button, and that high energy pulse is transmitted and the images are analyzed instantaneously in real time, and you can look at the color map of tissue stiffness that results. Now, unlike the static elastography color maps, here the blue tissue is the softest, and then firm tissue is going to variably be yellow, orange, or red. So here we have a soft benign mass and a firm malignant mass. The color map is uniformly blue for benign tissue, and it's what we call actually a tie-dye appearance, a mixture of yellow, red, and orange for firm malignant tissue. In addition to just displaying a color map, you can also see that the apparent size and shape of an image will be extremely different for hard tissue as opposed to soft tissue. So these are two malignant masses, the appearance in B mode, and then as compared to the appearance on the color map, which is considerably larger and more irregular for both of them. And another example of malignant tissue with a color map looking quite a bit larger and more irregular than the B mode image. Now, those are the subjective assessments of the mass with the color map itself. However, you can also do a quantitative assessment. So you activate, it's called the Q box. It's literally a region of interest that you can place over any part of the color map that you want. So if you place it on the stiffest portion, the most red portion, and then place another region of interest against the surrounding normal or blue tissue, you can not simply measure the actual hardest tissue, but you'll also get a ratio of the hardest to the softest tissue, and again in kilopascals, and in a very, very reproducible way. So how do we incorporate shear wave elastography into assessment of breast masses? Again, remembering our goal, we want to decrease intervention for benign masses, but we don't want to miss any cancers. Here's a lesion, which is, granted, it's not equivocal on mammography or ultrasound, but it's an example of how elastography can display malignant tissue. So this is a large, almost circumscribed mass, very characteristic of very high-grade cancers through transmission on the B mode image. And on elastography, the area around the perimeter of the mass and all of the surrounding breast tissue is markedly abnormal and markedly stiff, telling us that this is malignant. Here is a more subtle mammographic finding. This is a focal asymmetry, which was a change from prior studies. On ultrasound, we have a ill-defined, very inhomogeneous mass, mixed echogenic and hypoechoic. On color Doppler analysis, we see that there's lots of blood flow, so this is a suspicious lesion. And on shear wave elasticity, the appearance is a little bit more subtle. It's not uniformly blue, however. It's mostly blue, but with areas of pale blue and yellow. So this is not the most suspicious appearance for shear wave elastography, but definitely not typically normal. So it agrees with the mammo and ultrasound assessment that this is suspicious. So how can we use shear wave elastography and ultrasound? And I'm going to be looking at this specifically for our probably benign masses, masses that we would have called BI-RADS 3 or BI-RADS 4A. Can we use shear wave elastography to downgrade BI-RADS 3 to a BI-RADS 2, or can we downgrade 4A to BI-RADS 3? For this, we need to understand clearly what a negative elastogram is and what the negative predictive value of that is. And in order to accomplish this, there has been a multi-center clinical trial which enrolled 2,000 patients at various sites in Europe and North America. And the collection of data is still underway, but the preliminary analysis of the first 1,000 cases is very promising. The specific questions of the trial was to actually look at whether shear wave elastography can improve sensitivity and specificity. It also looked at whether the shear wave elastogram maps and values were reproducible and user independent, and if it could also reliably distinguish solid masses from cysts.